So this video is going to look at matrices, the basic properties and the basic operations. A matrix is the singular of matrices, and it's an array of numbers which can summarize a table of values if the context is known. The values are arranged in rows and columns and enclosed in a set of brackets. Matrix names are always capital letters. So here we've got the matrix A equals 1, 2, 3, 4, 5, 6, and matrix A is known as a 3 by 2 matrix, and it has 6 elements. So when you're asked about the order of a matrix, in general we class matrices as m by n, where m equals the number of rows and n equals the number of columns. The elements are the numbers inside the matrix, and they're described by their position within that matrix. So Aij is the ith row and the jth column. So replacing the 6 elements inside matrix A, you can see that A11 is in the first row, first column, A12 is in the first row, second column, and so on down to A32, which is in the third row and the second column. So the example from matrix A, state the order, the value at A13, and the position in the matrix of element 5. So the first thing we're going to do is we're going to count how many rows there are and how many columns there are in order to work out what the order is, remembering that it's m by n. So we've got 2 rows, so that goes first. And we're going to multiply that by the number of columns, which are 3. So our order of matrix A is 2 by 3. So we've then got the value at A13, and the position in that is in row 1, column 3, and so the value of A13 is 3. And then we want to find out the position of element 5, and you can see that that's in row 2, and it's column 1, so it's A21. So the transpose of a matrix is formed when rows and columns of the original are swapped over. So in other words, the first row becomes the first column, and so on. So the transpose of matrix A is denoted in 2 ways, either A to the power of t or A prime. So if A is the matrix A, B, C, D, E, F, then the transpose of A is going to be A, D, B, E, C, F. And we also need to note here that the transpose of A is the original matrix A. So there's 2 special instances with regards to our transpose of a matrix, and they can only happen with a square matrix, remembering that a square matrix has n squared elements. So if the transpose of A equals A, where A equals 1, 2, 3, 2, 4, negative 2, 3, negative 2, 5, if we take the transpose, so remembering that we're going to take the first row and we're going to make that the first column. So our first column of our transpose is going to be 1, 2, 3. And then we're going to go back and take our second row and make that our second column of our transpose. So that's going to become 2, 4, negative 2. And then we're going to take the third row of matrix A and make that the third column of our transpose of A. And that's going to become 3, negative 2, and 5. And this is classed as symmetric because you can see that the transpose is identical to the original matrix A. The second special case is if the transpose of A equals the negative matrix of A. So this time we've got A equals 0, negative 1, 3, 1, 0, negative 5, negative 3, 5, 0, and we want to find the transpose. So first row becomes first column, so that becomes 0, negative 1, and 3. Then our second row becomes our second column, and so that's 1, 0, negative 5. And our third row becomes our third column of our transpose, and that will be -3, 5, 0. So now you can see that every single term is multiplied by -1. So we've got the negative of the original, and this is classed as skew-symmetric. Now you can only have a skew-symmetric case if the lead diagonal values all equal 0. So that's A11 to A33. So we want to find A, B, and C if matrix A is symmetrical. So if matrix A is symmetrical, that means that our row 1 and our column 1 are going to be identical. So if we rewrite our matrix, we've got A equals 2, 0, -4 in our first row, and 2, 0, -4 in our first column. So A is going to equal 0 and B is going to equal -4. And you can see that our C value is in our second column, which has got to be the same as our second row. So filling in the details on the matrix at the bottom, our middle row, or row 2, is going to become 0, 5, 3. That's going to be the same as our second column. And then we've got 7 in A33 to finish our matrix. So C equals 3. So the second example here, we want to complete matrix B so that it is skew-symmetrical. The first property we need to remember is that the lead diagonal for a skew-symmetrical has got to have all values equaling 0. So if we write matrix B, we can fill in our lead diagonal with 0, 0, 0. And we can fill in the rest of the information that we've been given in the matrix at the top. So we know that in order for this to be skew-symmetrical, if we were to take the transpose of this matrix, we would need to have the negative equivalent of B. So considering the first row and the first column, we need them to be the inverse of each other. So we can fill in A12 with a -2, and we can fill in A31 with a -9. Then the other position that we need to fill in is A32, and that will have to be the inverse of the -4 in A23, and so the value of A32 is 4. So when we're doing matrix addition and subtraction, we can only add and subtract matrices of the same order. Because the process of addition, we simply add the corresponding elements from each matrix. So if they had a different order, then you wouldn't have elements that match up. So you can see here, for matrix A, B, C, D plus E, F, G, H, we get the resultant matrix of A plus E, B plus F, C plus G, and D plus H. For subtraction, we have to subtract the corresponding elements with the same process. So our rules of addition and subtraction are, due to the associative law, A plus B equals B plus A. However, A minus B does not equal B minus A because it matters which order you subtract, and the transpose of a sum is the sum of transposes. And finally, we're going to look at multiplication by a scalar. So if we have the matrix A equals A, B, C, D, then Ka, where K is a scalar quantity, is going to equal Ka, Kb, Kc, Kd. So each element is multiplied by the scalar. So we have our -2 multiplied by our A11 element. So we're going to get -6. Then we're going to get -2 times -5. So we're going to get 10. -2 times 7 gives us a -14 in A21. And -2 times a half gives us a -1. And so our scalar matrix, when we're multiplying it by -2, is -6, 10, -14, -1. So finally, we're going to solve this example, bringing together our basic properties, our addition, subtraction, and our scalar multiplication. So the first thing we want to do is we want to isolate the 3x because we eventually want to get x on its own. So we need to do the inverse of take away the matrix 1, 4, negative 2, 3. And we're going to add that matrix to both sides. So 3x is going to equal 8, 11, negative 1, 0. And we're going to add on the 1, 4, negative 2, 3. So 3x is going to equal 8 plus 1 gives us 9, 11 plus 4 gives us 15, negative 1 plus negative 2 gives us negative 3, and 0 plus 3 gives us 3. Now we have a scalar of 3, so we need to divide both sides by 3 to isolate x, the matrix, on its own. And so 9 divided by 3 gives us 3, 15 divided by 3 gives us 5, negative 3 divided by 3 gives us negative 1, and 3 divided by 3 gives us 1. So our matrix X is 3, 5, negative 1, 1.